This is part 6 of the series Circumference and Area, and in this part we're going to look at composite figures. Specifically, we're going to look at area of composite figures. Now, a composite figure is simply a figure made up of multiple geometric figures. In this example, we're given a composite figure which is made up of a regular hexagon with side lengths of 10 and two equilateral triangular attachments on the left and the right. So there's the regular hexagon, and these are equilateral triangles. All right, let's jump in and see what kind of information we have and where we need to go from here. Well, probably the easiest place for us to start is finding the area of this regular hexagon, because we just got finished doing that. So let's go ahead and do that. Let's draw in our bottom triangle here, just like we always do. And we'll draw in our apothem. And we'll draw in our values. It says we have a hexagon with side lengths of 10. So this side length is 10. Therefore, this has to be 5, as we've talked about in the past. And we're looking for our apothem. Well, the idea here again, this is a hexagon. So we know that our central angle here is going to be 360 divided by 6, which is 60. And if the whole angle is 60, this angle has to be 30. So we have a 30, 60, 90 triangle. So I'm going to assume at this point that you've got your 30, 60, 90s down from our regular polygon discussion. So we're going to say this side is A, this side is 2A, and this side is A square roots of 3. Well, that's all we're concerned about is this side here, because we already have this side length. So that means our apothem is A square roots of 3, and A is 5. So our apothem is 5 square roots of 3. That's our apothem. Now, let's go ahead and write down our form for the area. That's 1/2 pa, and that's area, which gives us 1/2 perimeter is side length, 10, times the number of sides. Since it's a 6-sided shape, it's 6, times our apothem, which is 5 square roots of 3. And this is going to be an approximate value because we have a square root of 3 here. And so we're just going to put that in our calculator. And I'm going to store this. Let's call this area H. And I'm going to store it in H. On my calculator, I have 26. If you have a different calculator, then just use 1, 2, 3 or ABC or whatever you want, but just make sure you circle where you store that area, because we're going to need that to add it to these two areas as we move forward. So let's calculate that, and that's 259.8 approximately, but I've stored that in H. All right, now let's see if we can find the area of these two triangles. Now, since these are equilateral triangles, this side length equals this, and these three sides are the same length, so these two triangles are going to be congruent triangles, which means that's all I really have to do is find the area of this triangle and then multiply it by 2. So let's draw the triangle in here, see if we can't figure out what we've got. We know that the side lengths are 10, so this is 10, 10, and 10. Now I'm going to put in the altitude here because I know the area of a triangle is 1/2 base times height, and that value is the height. Well, if this is 10, then this has to be 5. And since this hypotenuse is twice the smallest side, it appears that this is going to be a 30, 60, 90 triangle. And in fact, since it's equilateral, I know that this angle has to be a 60-degree angle. Therefore, since this is 90 and this is 60, this has to be a 30-degree angle. So this is a 30, 60, 90 triangle, and therefore this hypotenuse is simply the apothem. It's the apothem that we got from our original problem here. If you notice, this vertex touches right there, but you didn't have to know that to calculate it. We just calculated it ourselves and verified that yes, in fact, this segment is exactly the same as the length from the center of the polygon to the opposite side, which is the apothem. So our h is equal to 5 square roots of 3. Now the area of this triangle, we'll call that AT, area of triangle, is 1/2 base times height, which is 1/2 10 times 5 square roots of 3. That gives us the area of the triangle, and our composite area is going to be made up of all these. So I'm going to go ahead and calculate this and store that into t. You can store that in any other value you want. That gives us approximately 43.3, and I stored that in alpha t. I stored that in memory location t. All right, now the area of our composite figure is going to be this area, the area of the hexagon, plus 2 times the area of the triangles. So our area composite is h plus 2t. And these were the values that we stored in memory. So that's going to equal approximately 346.4. Now, it should be noted, if you're fond of just finding the area of the triangle and multiplying it by the number of triangles, the area of one of these triangles, this triangle is exactly the same as that triangle there. So that's all you really had to do to find the area of this composite, is find the area of this triangle in here, this one down here, and multiply it by not 6 for 6 sides, but by 8, because there's 8 total. And you would have gotten the exact same thing. So if you take AT and multiply it by 8, you get the same number. All right, let's move on to another example. This problem exhibits one of the hazards of being colorblind. We have this composite figure here, which looks fine to me, but you might find this incredibly ugly. But that's okay. Hopefully you'll be able to work through the pain. What we have is a 60-degree sector of a circle, 60-degree sector of a circle whose circumference is 16 pi. We have a square attached to the right side of the sector, so this is a square, and a semicircle attached to the top. So let's begin and try and figure out how to find the area of this beast. We're going to start with the sector because that gives us our primary source of information. We know that it's a 60-degree sector, so this central angle here is going to be 60 degrees. And the circumference of the circle this is a sector of is 16 pi. So let's start with that circumference and see where that leads us. Clearly we're going to be finding radius. So circumference is 2 pi r. The circumference is given to us as 16 pi, which is 2 pi r. We're going to divide both sides by 2 pi. So 16 pi divided by 2 pi equals the radius. Oh, happy day. We can cross out the pi's. 16 divided by 2 is 8 equals r. So the radius is 8. Now we can take that radius and we can go ahead and find the area of that sector. Now if you recall, area of sector of a circle, area of a sector is to area of the circle as central angle is to 360. So the area of the sector, which is what we're looking for, is to area of a circle. Remember, McDonald's pi is r squared, so it's pi r, which is 8 squared. Central angle, it's a 60-degree sector, so the central angle is 60, is to 360. Now we just have to multiply both sides by this quantity, and we get area of sector is 60 times pi 8 squared divided by 360, and that comes out to approximately 33.5, and I'm going to store this in S, and I circle it because that tells me what variable I've stored it in memory. You can store it in whatever you want. Alright, now let's take this information and see if we can determine the area of this square. Alright, well, the area of the square is fairly straightforward because we found our radius of 8. So this side length is going to be 8. So the area of our square, then, is going to be 8 squared, which is 64. So that one's pretty easy. Now, our semicircle, well, this half a circle, and we know that the area of a circle, since area of a circle is pi r squared, then we know that the area of this semicircle is pi r squared divided by 2. So the area of half the circle is pi r squared divided by 2. And now since this length of the square is 8, the radius of that circle is half that length. So the radius is 4. So that gives us pi 4 squared divided by 2. That's 16 divided by 2, which is simply 8 pi. Now we have all the information we need to find the area of our composite. So the area of our composite is simply this sector. So it's the S value that we stored plus the area of the square, 64, plus the area of the semicircle, 8 pi. And if we put this in our calculator, we will get approximately 122.6. All right, well, we have one more composite example to do, and we have one more section. So we're going to go ahead and finish the last composite in the next session, and we're going to wrap up this series in the next video. So I will talk to you in the next video.